This week we are weighing Duracell.
My name is Matt. Follow along as I turn Duracell, the legendary ocean racing sailboat, into a comfortable cruising home.
Last week we built the cradles. Before we weigh the boat, I'm going to explain why we're weighing Duracell. This is a really fun topic for me, and we're going to get a little nerdy about why it's a necessary step in making Duracell a fast and safe cruiser. In the second half, we're going to weigh the boat, which was a pretty exciting and pretty nerve-wracking project. I'm going to try to explain the basics of stability, riding moment, and trim with Duracell as the subject of our explanation, with the caveat that I am not an engineer or naval architect or physicist. I'm an enthusiast doing my best to learn from them. So if you are one of those, you're welcome to roll your eyes or yell at the screen as I fumble my way through this explanation. Evan, the naval architect, has been integral in helping me understand all of this. And of course, your comments, constructive comments and questions are very encouraged. As a reminder, our goal in this project is to make Duracell a safe, practical, comfortable, and fast cruising yacht. The boat was built to be a fast and safe racing yacht with the emphasis on fast. We want it to be a comfortable liveaboard, so we have a lot of modifications to make it comfortable while retaining speed. One of the major changes to the boat will be to modify the keel. The original keel has been sitting on its side like this for more than 25 years. It is a 10-foot long steel and lead fin keel with a lead bulb at the bottom, and it weighs in at around 11,000 pounds. It is too long for practical cruising, not to mention in too much a state of disrepair to use again. So we'd like to shorten it so that the overall draft of the boat is more like 8 or 9 feet as opposed to the 12-foot draft I had before. A shorter draft allows us to anchor in a lot more places while cruising. Let's get into how shortening the keel affects the safety of the boat. This is a very complex topic, so in the interest of time, it will be a very surface level discussion. Now, a stable boat that can keep itself upright against the forces of wind and waves is a very safe boat. A boat's stability is affected by its form or its hull shape, its weight, and more importantly, where the weight is concentrated. This is very simply illustrated by a section view of Duracell. Let's also show where the weight is concentrated vertically, or the center of gravity, and its center of buoyancy. These two forces are directly opposite when the boat is sitting calmly at anchor. As Duracell heels, the center of buoyancy moves as the boat heels, and the center of gravity remains in the same position, with the force continuing to point to the center of the earth. And as the boat heels, the horizontal distance between these two forces grows and creates a force called the riding arm. The length of the riding arm is the amount of force the boat exerts to right itself. The riding arm grows as the boat heels, but not forever. At about 45 degrees of heel, the riding arm length maxes out, and if we keep heeling, it actually starts to shrink and continues to shrink until we reach what's called the angle of vanishing stability. At this point, one more degree of heel and the boat will capsize. And in theory, if the boat is in totally flat water, for instance, the riding moment will be back to zero when it is upside down. These angles are graphically represented on what's called a riding moment curve, which shows how much riding moment there is at every degree of heel. This is a very complicated calculation because finding the center of buoyancy for every degree of heel takes forever, unless you have a good computer program. We can learn a few things from the riding moment curve. The slope at the beginning of the curve shows how stiff a sailboat is. Where it crosses zero riding moment is the angle of vanishing stability, and the area under the curve represents how much energy it takes to capsize a boat. And the area under the negative riding moment is how much energy it takes to right a capsized boat. It is very unlikely for the wind alone to push the boat over all the way to its angle of vanishing stability because wind is dumped out of the sails as it heels. But a large breaking wave on the beam does have that power. And so this area under the curve is the amount of energy a wave needs to capsize Duracell. So to sum up, we want this area to be big and broad, this area to be small, where it crosses zero somewhere above 120 degrees, if not 130 degrees. Evan has even been modeling how Duracell will perform at these high degrees of rotation. If we heel Duracell at 30 degrees again, we can illustrate how changing the position of the center of gravity by making the boat heavier or by putting the weight lower affects the riding arm as well. If the weight is moved lower or closer to the bottom of the keel, the riding arm grows even more. If it's moved up, the riding arm shrinks. By turning Duracell into a cruising boat, we are inherently going to make the boat heavier, which will lower the center of gravity and help create more riding moment and allow us to reduce the length of the keel. So all this to say that the weight, and more importantly the position of the center of gravity, is extremely important to know accurately before keel design begins, so that we can design a safe yet fast and practical keel for our boat. There are a few constraints before we begin deciding on keel weight and shape as well. The first is the new mast. We cannot add so much riding moment that the mast will collapse under the weight of the riding moment when we're fully loaded. This is another long and interesting conversation we'll have to get into later. The other constraint is the weight of the rest of the boat. The weight of the hull, the doghouse, the interior I've built, plus everything that will be installed, including the mast, the dinghy, the refrigerator, engine, cat box, tools, and everything else has to be accounted for. This is done in what's called a weight estimate. This is a spreadsheet that adds together every item on board and its position in all three dimensions. The results will be the total weight plus the estimated position of the center of gravity, emphasis on estimate. I've tried to keep track of every piece and part I've installed.
So this is the final weight of the first chain plate that we've finished. It's all cleaned up and everything. So this one weighs just under 10 pounds.
But I've forgotten more than once to weigh stuff as it goes in. Plus, keeping track of all the taping and epoxy is tedious work that I sometimes don't have the patience for. So again, it is an estimate, but the weight of the finished boat with all its stuff needs to be as accurately assessed as possible before we can determine the characteristics of the keel. While the center of gravity vertically will contribute to determining the riding moment, the center of gravity fore and aft will change the boat's trim. For instance, if my changes to the boat make the center of gravity too far aft without changing the position of the keel, the boat could trim aft and bring the bow up. To fix this, we can simply adjust the ballast forward on the keel to trim the boat back onto its lines. I spent weeks this past winter doing a proper weight study, and I was happy with the results. The hull, I estimate, after all my modifications, should be about 10,300 pounds, and after we install everything, fill it all up with water and fuel, and put the keel on, should come out to about 35,000, which is about 5,000 pounds heavier than Duracell was in racing trim. A good compromise. Then I met Paul. He convinced me that the weight estimate isn't good enough, and that weighing the boat would be worth the effort to know for sure how much change I had made to Duracell. In order to get the most accurate measurement, I took everything off the boat. I got all my tools, supplies, and parts taken off so that the boat was totally empty, and I was just measuring the weight of the hull. My cradles are done. The day has come where I get to weigh the boat. I'm pretty nervous about it because I'm literally jacking the boat up. I'm only doing it a little bit, just enough to free the jack stands and the dunnage that's under the keel, but still I'm moving the boat up. It potentially weighs, well, the estimated weight is around 10,000 pounds, and so it's a lot of weight to be moving up, and the worst thing that could happen is that the boat tips over fore or aft, especially. But
that would be very bad, honey.
Oh yeah, of course it would be.
I mean,
especially if one of us was underneath it.
Yeah, I just want our viewers to know that Matt just told me it's important, honey, that you have an escape route.
Yes.
Where's my escape route?
Just along the side here. Just if I say timber. Timber.
I don't know about this. Please don't fall, Duracell.
Let's do it. Let's get this over with. It's a necessary step, and I'm feeling pretty confident about it. I'm still nervous, but I'm confident about it. How it's going to work is we're going to get all the weight on both cradles. The scales are going to be under one cradle, and we'll weigh that side, and then we'll switch them. And the scales will be on the other side. You add those two numbers together, and that's the weight of the boat. This is the scale that the local shipwrights co-op let me borrow. And it's actually 2 scales. They're called load cells. They have 100,000 pound capacity. And so I'm going to get one on each end of the cradle and add the 2 numbers together, and that will be the weight of that side of the boat. So thank you very much to the Shipwrights Co-op and Paul for getting this to me so I can do this project. All right, so I'm going to start jacking this up. The trick of this whole thing is to get the boat off of the jack stands and the weight onto the bunks or cradles. And so there's a lot of weight on, especially these aft jack stands, and there's a lot of weight on the keel here where that's blocked up in the middle of the boat. So what I'm using is this, it's called a pancake jack, and it's just like a really, really short jack, and it's a 10-ton jack. So should be more than enough to lift the boat up at each corner and get the weight up off the jack stands.
Hey, honey.
Hey.
I feel like there might be some viewers watching now who are like, are they gonna like get squished by the boat? What idiots. And we're gonna get some like really intense comments. Is there anything you can do to assure our viewers and frankly me right now that we're safe?
Yeah, I wouldn't do this if I didn't think it wasn't safe.
Okay. I trust you. I do.
Okay.
Let's do it.
Let's do it.
Hearing some creaking.
Mm-hmm. This one's loose, but this one's not.
I don't know if I've ever seen you this nervous. Did you just say it's my boat?
It's my boat. I gotta take care of it.
I do trust Matt. I really do. He's a very, very cautious, careful guy. Are they all loose now?
Yeah, just this side, but I can do the same on the other side.
Woo. Thanks. I don't know if you can hear that, viewers, but
There's a lot of creaking happening.
So as you can see, all the weight is now off the stands. It's pretty much all in the cradles. I'm trying to get the cradles jacked up just like a 1/4 inch is all I'm trying to get them up even just that high. Mostly so that I can get this block out from under that keel beam and getting the weight off of that I-beam there.
can hear the cradles like taking on weight.
Yeah, they're like settling. So I'm jacking up this forward cradle, which is trying to pivot on that aft cradle. So there's 2 cradles. The boat's pivoting on this. As I lift the forward one up, the boat is pivoting on that aft one. And so I got to make sure that the jack stands that are aft of that cradle are not holding it up, like they're not standing up onto the boat is not standing up on those jack stands. So I'm constantly loosening them up to make sure that they stay away from the boat just a little bit.
There's air.
Huh?
I'm just looking at how there's now air between these jack stands and Duracell's hull.
So I've jacked the boat up 1 full inch at all 4 corners, at all 4 ends of the cradles. All the cradles are loose, and this block is also loose. So it's time to actually weigh it. According to the weight estimate that I have from Roger Martin, the original build weighed 9,080 pounds, and that is just the hull with the bulkheads and the deck and the superstructure, anything glued and laminated to the boat, no rudders or keel or rigging or machinery, anything. It's just what's glued to the boat. So the original estimate was 9,080 pounds, My new estimate after cutting a bunch of stuff out, gluing, building a bunch of new stuff is 10,272 pounds. So I'm guessing that we're going to be exactly that, 10,272 pounds.
Confident.
We're going to find out here. So how this works is I've got the forward bunk on these triangle pieces so that it's like the forward bunk is just on 2 points. So that it's basically pivoting on that forward bunk. And then the aft bunk will have the load cells underneath it. So right now I've got the first load cell placed under this side. After I lower the jack down, I'm going to go and put the other load cell in on the other side. And then actually I'm going to switch them. So we'll take the measurement, switch them, and take the average. And then we got to switch everything so that I can weigh the forward end of the boat. So here we go. I'm about to ease down the jack, and it should go up a whole bunch.
Easing it down now.
My cement pad is like compressing into the ground. Oh, wow. So 7,000 pounds on the aft end, the aft cradles. This is the last test. I've got the port side load cell loaded, and so I'm about to ease down the starboard side so you can watch the numbers. So that second test was a lot different than the first one. 600 pounds different. The total I got is 11,500 pounds. Now that includes both cradles as well as the beam that's attached to the keel. And so I got to figure out the weights of those and subtract that. But it looks like it'll be somewhere around 11,000 pounds. We successfully weighed the boat without dropping it, as you can see, or knocking it over. And the final weight came out to 11,330 pounds. I did a bunch of measurements, swapping the load cells around, and that's the number that I landed on. It is about 1,000 pounds heavier than my estimation was, and that could be for any number of reasons. My estimating could be bad. I was basing my estimates on old weight estimates from when the boat was built, and who knows what modifications could have been made to the boat in the meantime that changes those weights. But the bottom line is I'm really glad that we did the project to weigh the boat, because now we have more accurate information moving forward in the keel design area. So, and the center of gravity ended up being pretty close to where we thought it was going to be, just aft of center. So now we can move back to actual boat projects, which I'm really excited about. We have a bunch lined up for the summer that I'm really looking forward to. So thank you again very much for watching. We have a few new Patreons to thank this week.
First, thank you to Elle or Ellie and Tanya. They just got done cruising for a couple years on the East Coast on the Intercoastal Waterway on their 34-foot American tug with their dogs Toby and Chester. Their boat's name was Portkey, a Harry Potter reference. So thank you very much to Elle and Tanya. Also thank you to Tom, who lives in Texas now, but used to sail a lot on Lake Michigan. He had a Hunter 27, I think he said, as well as a Chris Croft that him and his wife fixed up. And lastly, thank you to Peter. He was a seafarer his whole life, sounds like, doing on big ships, and also did a lot of sailing out of South Africa, and now resides in Germany. So thank you very much to Peter. And thank you to everybody, of course, who's been helping with the project. We couldn't do this without you. And as an update, no baby yet, but any day now.